Hi guys, and this is going to be a video about Kepler's laws of planetary motion. We've been talking about circular motion the past couple of days, and this is just a little extension to that same kind of topic. We're not going to do any math with this per se, but I'd like for you guys to be introduced to these laws of planetary motion, and they will show up on your test. Some of you guys that are in AP Euro probably have already heard of Kepler and are familiar with these laws, but for those of you guys that aren't, we're going to go ahead and go through them, and maybe you'll learn something even if you've heard of them before, or maybe learn about them in a little bit of a different way. So, first of all, let's discuss who Kepler was. Johannes Kepler, he was a German, and he was an astronomer who worked very closely with a guy named Tycho Brahe. Tycho Brahe was Dutch, I believe. Maybe he was Danish. Can't remember that part. But they worked together in the late 16th century, and they were looking at planetary orbits and how things moved in the sky. Now, he had come up with a theory as to planetary orbits in 1596, but it wasn't correct. Now, Johannes Kepler and Tycho Brahe, Tycho's probably my favorite astronomer ever. He's crazy and really out of control. If you guys have an opportunity to look up some stories about him, they're pretty insane. He got in a fight and a duel, and he got his nose cut off. So he had a golden nose made, and he would wear this golden fake nose all the time. There's tons of paintings with him wearing it, and he's just really crazy. But Johannes Kepler was his partner, and they developed what are now known as Kepler's laws of planetary motion. And they worked together for a big chunk of their life, but Kepler was the one responsible for the laws, so they're named after him. Okay, so here are Kepler's laws of planetary motion. They describe how planets orbit around the sun. The first one says that the orbit of a planet around the sun is elliptical. The second one says a line joining a planet and the sun sweeps out equal areas and equal intervals of time. And I'm going to explain what that means here in a second. And then the third one, which is probably the more lengthy one to explain, is actually very easy conceptually. The square of the planet's sidereal year is proportional to the cube of the length of its orbit's semi-major axis. That's a mouthful. All right, so let's talk about the first law first. And the first law says that all planets' orbits around the sun is elliptical. Now, I want you guys to understand that by the term elliptical, a lot of times you'll see the Earth's orbit, or any planet's orbit, if this is the sun, and I guess the sun is green now, you guys will see it sometimes drawn in books like really, really super highly elliptical. And it's not really like that. It is really close to being a circle. It's just only slightly elliptical. And that's a pretty poor drawing there of that too. But the eccentricity, or the amount of ellipticalness of the orbit, is not this exaggerated. I think they do that just to drive home the point that it is an ellipse. Because if they drew the actual orbit of the Earth around the sun, it would look fairly circular to us. All right, the measure of how elliptical the orbit is called the orbital eccentricity, which is what I just mentioned. So this is done on a rating from 0 to 1. So an orbital eccentricity of 0 means that it's practically a perfect circle, and 1 means it's almost a straight line. So here we have a large eccentricity orbit, and down here we have a smaller eccentricity orbit. Now, as the planets get further and further away from the sun, their eccentricity increases. All right, the second law describes the sun being at the focus of the ellipse. Now, if you guys remember from math, every ellipse has 2 foci. And Kepler said that the sun has to be at one of them. So this means that as the planet swings around the sun, there are regions where it's closer and farther away. So let's look at this. Here we have 2 new vocabulary words you guys might not know. Perihelion means when the planet is closest to the sun, and aphelion means when the planet is farthest away from the sun. I like to keep it straight by saying A stands for aphelion, which is also away. So A, away, it's farthest away from the sun. All right, so this is our diagram, right? So over here, when the planet is close to the sun, that would be perihelion. And over here, aphelion. Now, the second law says that a line joining a planet and the sun sweeps out equal areas in equal intervals of time. So what does that mean conceptually here? Let's draw our little sun. Ooh, I don't know if you guys can see that very well. I'm going to draw the Earth over here. And again, I'm going to highly exaggerate this elliptical orbit for the purposes of what I'm explaining to y'all right now. Ooh, there we go. Okay, so he says that there is an imaginary line that goes from the sun to the planet, let's pretend, and that this line has to sweep equal areas in equal amounts of time. So let's say my planet's right here at this point that we will call point 1. And over the course of a couple of days, let's say my planet goes to point 2. So let's look at how much area of space my planet has covered. My planet, in that time frame, has covered this much area of space. And let's assume that this distance from point 1 to point 2, let's say that took my planet 2 days to do. So fast forward to much later in the year when the planet is over here on this side of the sun. And let's call this position point 1 over here. Now, according to Kepler's second law, the planet has to still cover this much area in 2 days. So over here on this side of the sun, my triangle has to become much shorter because I'm closer to the sun. So in order for me to get the same area, that means my triangle that I'm making in the sky has to be much wider. Right, so now if these two areas of space that I'm moving through are the same, what does that mean for the distance I've traveled actually in my orbit? That means, oh sorry, I guess this should be point 2 and this should be point 1. Sorry guys. That means that I've traveled a greater arc length here than I have here. My area is the same. The black regions end up mathematically being the same area, but the arc length over here is much larger because my triangle is much shorter. Over here I have a very long skinny triangle, over here I have a short fat one. So what does that mean? That means that planets speed up when they get closer to the sun, and they speed up because they have to cover the same amount of area in the same amount of time. They have to go faster to make this arc length distance. Planets travel faster at perihelion, slower at aphelion. And again, this is the picture that I just drew, kind of sort of for you. So here we have two equal areas, and the planet, of course, is going to have to speed up because it has to cover this much distance instead of this much distance. All right, Law 3 says that the square of a planet-side real year is directly proportional to the cube of the length of its orbit's semi-major axis. In plain English, that just means that planets closer to the sun have shorter years than planets farther away from the sun, which makes sense, right? We have our solar system with Mercury closer to the sun. Its orbital period, or its orbital year, a planet's orbital period is the time it takes for it to go around the sun once, so that would be its year, is going to be much shorter than, say, Pluto's, which Pluto is not really a planet anymore, but we're still going to count him for this. Even shorter than Neptune's, rather. Alright, so mathematically, if we wanted to come up with a proportion for this, what we see is that the cube root is proportional to the square of the year. And this ratio holds true for every planet in the solar system. So if I wanted to compare Mercury's radius and year to Pluto's radius and year, and now this is radius of the orbit, right? Not radius of the planet, but radius of the orbit. these two ratios would be equal. And for every planet in our solar system, it ends up being about 3.34, roughly, that number here. All right. I believe that is, oh, here's an example. Of course, the elliptical orbit is greatly exaggerated at this point, but here's your perihelion place and here's your aphelion place. And the longer this axis is, right, from the planet to the sun, the longer your year is going to be. All right, guys, that's all the notes I have for you. I will see you guys on Monday.